Hello, and welcome back to Remoticon. I'm Jasmine Brackett, and I run Tindy Hackaday's hardware marketplace. I'd like to introduce our next speaker, who is a science communicator and electronic engineer. Although we're both from the UK, I think I first met him at Bay Area Maker Fair around 2015, where he gave me this very, I don't know if you can see it, very cute. No, my background's, oh, I'll take a picture and put it in the Discord. Super cute monster to learn to solder monster. Since then, a lot has happened, especially in open source ASIC, and particularly in the last year. We're excited to have Matt Venn speaking at Remoticon this year. I hope you enjoy his talk, Open Source ASICs, A Year in Perspective.
So yes, Hackaday Remoticon. Nice to see you all. Shame it's not SuperCon, but we've got Remoticon instead. Can I get a mic check in the channel? Is my levels okay? Not too loud, not too quiet. Let's see. Nobody is saying anything. Oh, there's this 10-second lag anyway, isn't there? So yeah, so probably quite a few of you saw my Remoticon from last year, 02 ASIC demo, where I showed the open source ASIC tools in full effect, and that talk is still available on the YouTube channel. Nice mugshot, level perfect, spot on, works great. Excellent. Okay, I'll stop watching that now, otherwise it will distract me. Yes, and yeah, a lot has happened. So I went from 0 to ASIC myself. And I've just done my third tape out, so I've done 3 chips now. Still haven't got any, but I'll explain more as we get along. And the title of my talk is called Open Source ASICs, A Year in Perspective. And I'm going to try to keep this broad, not just about my experience, but about other people's experience, and also about different kinds of initiatives going on around the world. And I'll take these off now as well. So now I'm going to share my screen. There we go. Okay, I've got my laser turned on. Everything is looking good. So just a little recap. I've got to start the timer as well. I originally got interested in the ASIC toolflow when I saw Tim Edwards from efabless presenting a design he'd done with Qflow, which is a tool chain that he maintains. And I ran one of my FPGA designs through that and got a GDS and posted it on Twitter, and that was cool. But probably it would have ended there had it not been for the announcement by Tim Ansell in June on the FOSSI dial-up talk, talking about the open source PDK, the new open source tool chain, and a free shuttle opportunity. So I looked into how much it costs to get a chips made, and it was like $20,000. So I kind of thought, oh, well, I'm not going to do that then. And then Google said, okay, we're going to sponsor 6 shuttles, and they'll be free as long as your design is open source. So I was totally on board with that. So I immediately ran my VGA clock FPGA design through the OpenLane tools, got result out of that. Worked hard to kind of work out what the limitations and how to install the tools, worked on a demo for Remoticon. There was loads of love on Twitter for learning more about that, so that was really great. And actually, I wanted to say thanks to all the people who watched the Remoticon talk and gave me support and encouragement to make my course, which I've done this last year, because I probably wouldn't have done that without the encouragement. And then I did my first tape out in December, and that was with efabless. So we've got the open source PDK, and what that is like a big database of all the things you need to know to be able to make a chip. So that the models, the timings, the parasitics, kind of how thick the traces need to be, the DRCs. If you've ever done PCB designs before, you've got all these rules like how close the metal needs to be, or if like metal is overlapping, then that's a DRC problem. So you have the same thing with designing microchips, but it's maybe like 5,000 different rule checks for a process like 130 nanometers, like the Skywater one. We had the open source toolchain OpenLane, where the idea is you put your design in your hardware description language like Verilog, and out the end comes GDS, and the GDS is the file that you send to the foundry, and in this case that's Skywater, and then they make the chips. And it's kind of about 40 layers for the Skywater PDK, so a bit more complicated than the PCB, and a lot smaller as well. And so we had this opportunity for a tape-out. This is on the side here, but I think number 5 was my VGA clock. So one of the things that was surprising to me was just how small this stuff is. And so I got some friends of mine to get involved. So I did 3 of these and had 5 other people. And then block number 9 was a multiplexer. So the Pico RV32 RISC-V processor living in this block here that's provided by efabless, as well as the pad frame, all the IOs. That enables the different projects to have access to all the IO pins. So they're not having to kind of share all the IO pins. They get complete access when they're switched on. So yeah, one other thing I should mention is these slides will be available, and there's loads of links here to get involved and follow what you're interested in. So just check the slides out at the end if you're interested. So looking a bit deeper into MPW1, there was 40 slots. So it's a really fantastic opportunity because the mask set for a wafer is about $200,000. And the way that you make that more affordable is you do a multi-project wafer. So you get 40 designs on there, and then you split the cost between all those 40 designs. But Google is covering the cost for that. So that kind of really lowers the barrier to actually get silicon in hand. It was oversubscribed, but they did find a way to make them all. And really, amazingly, 60% of the designs were by new designers, people who'd not done ASIC designs before, and that includes me. And this was my design. And then these other ones with the pink highlights were designs by people that I later interviewed. So if you want to find out more about those, then you can check my website. My personal faves from MPW1 is the Pi 5 USB peripheral designed by Sylvain Minot, TNT. He was on Hackaday recently for his Doom on an ICE 40 FPGA. And this is a really cool bit of work here. It's a microcoded USB stack. So the idea is with the firmware of the Pico RV32, you can specify how you want the USB device to work, and that configures all the endpoints. But then the hardware design and these blocks of memory here do all the buffering and all the hard timing. So I'm really hoping to use that in my own projects in the future. And then on the analog side, pick Thomas Parry's 5 gigahertz satellite transceiver. This is a really beautiful looking bit of analog layout, which is a PLL. And it's a nice bit of mixed signal. You've got a bit of digital stuff that is configured with the RISC-V processor, and that sets up this PLL. And the interviews are there. Now, another thing that I want to mention is OpenRAM. So OpenRAM provides the SRAM blocks. We've got 2 kilobytes of SRAM down here in the corner. And we need this really because if you don't have a RAM generator, then you're forced to use flip-flops. So Yosis, if you're used to any kind of FPGA stuff, you make a register and then Yosis synthesizes it out of 32 flip-flops. And you see how big they are compared to a bit cell. So Matt Goodhouse presented at FOSSI Dial-Up again. There was this great series of talks, I really recommend it, showing how OpenRAM works. It's parametric. You can have like dual port, single port, different sizes. They included 2 kilobytes of SRAM for the management area. We unfortunately don't get access to that from the user project area, although that is something that we're working on. I'll talk more about that later. So we thought we'd finished with the tape out, but in fact, there was a problem. Google had paid for an expensive tool called Calibre. So they had one license of that running on a Google server. And when they ran the designs that we submitted through it, it picked up some DRC errors. And here we've got these horizontal lines here that are power and ground, providing power to the macro block. So if you imagine my VGA clock, maybe this is a counter bit coming up getting routed on metal 5, going down through a via, and then going on metal 4 again. And then it was short-circuited to the power or ground here. So it was going to cause a terrible problem. And the Caliber program spotted that. So we were able to go back, fix this stuff. It was a problem with the configuration of the tools we needed to turn off to make sure it doesn't root on metal 5. In February, I had fun pretty printing GDS files. So 2021 has been the year of sharing GDS files. So if you're an ASIC designer, you've probably got a photo or a printout on your wall of your latest chip, but you're not really allowed to share that because you're having to sign an NDA. You're not allowed to share this information. And I had a lot of fun coming up with color schemes and printing this out and making badges like this one. Yeah, really enjoyed that. March, we had Strive come back. So Strive was a test chip that efabless brought up, and that tested a bunch of the kind of management stuff that is going to come with every chip that you make. So like I mentioned before, we've got the pad frame, we've got some SRAM, we've got a RISC-V processor, and all that stuff gets bundled for us by efabless. So we can put our design in the middle, and then we get this support, use a logic analyzer, be able to configure the GPIOs, that kind of stuff. So they tested a bunch of that. They sent that off in 2020. We got the chips back in March 2021, and we've got the obligatory blinky here. So that kind of showed that everything was working. That gave us good confidence of the tool chain and everything was working. In May, Chiplgnite was launched. So that's a commercial version of the free shuttle launched by efabless, which is $10,000 for 300 parts, which works out at roughly 33.333 recurring dollars per part. $10,000 is still a lot, but it's quite interesting because if you could share that space with a bunch of other people, say 16 different designs, then your cost for entry to get guaranteed silicon is down to 625. So just to make it clear that the Google have sponsored this free shuttle, and your design needs to be open source down to the GDS. It's a lottery system, so if there's more than 40 for a shuttle, then they have to pick the ones that go in. But this is a paid version where you're guaranteed the silicon and your design doesn't have to be open source. And this is maybe half the price that it was when I first started looking at the possibility of taping out on my own. So that the Chiplgnite program has been used a lot by universities. There were some early customers, and we've also seen the open source FPGA Foundation launching an initiative called TapeOut World. That's been launched in several countries. It's a university program. They recruit a champion in the university that builds it up and helps with the training. And then they use Chiplgnite to tape out projects. So the furthest they've got along so far is in Pakistan, where they've got 400 students trained up, and now they're going to tape out 12 projects. So that's super exciting. Great to see academia getting on board with that. In June, we had MPW2, the second tape out. We had 39 out of 40 slots filled. You can check this link to see a list of all the projects. My faves I'll talk about a bit later on. This was the design that I taped out down here. One thing that's quite interesting is when you look at these, you can kind of tell the difference between analog designs, because they're the really empty white ones, and the digital ones, which are the ones that are kind of completely full up. So by this time I'd made my course. I had some people on the course, and we'd taped out 2 of my designs and 14 designs from people on the course. Things were much improved. I wrote some tools. I had such a scary time with MPW1 because I was basically doing everything by hand. And this is a Python tool that aims to automate everything. So it can run all the tests on all the designs. It can check the firmware. It generates the configuration file. It does a whole bunch of different things. And then you can just run a make command, and you get the final GDS that you can then apply to efabless. So that was really fantastic. Super proud of that, getting so many people through this. A lot of people there really had come from zero with not even any digital design. So it was really good to see them go all the way through to the end. My top picks of MPW2, it's always difficult to choose favorites, but Fuse RISC is awesome. This is using the fabulous FPGA framework, which is a parametric FPGA fabric sitting in between two RISC-V processors. And one of the cool things about fabulous FPGA is it kind of comes with automatic support for YOSIS and NextPNR. So they're expecting to just be able to load a bit stream straight into this and be able to accelerate stuff between these two processors. And I think it's kind of easy to think like, okay, you've got your RISC-V processor, you've got a bit of FPGA fabric, and you've got some mixed signal like the radio transceiver we've seen from Thomas Parry, and there's some really powerful stuff we can start doing here. We saw the award-winning bit serial RISC-V processor from Ulov, and that was turned into a system on chip by Class and called Subservient. And a nice project by Lakshmi, who I had previously interviewed for her PLL project on MPW1, and she taped out an analog neuron project. So a little word on the work that Klaas did. Klaas and Ulov worked on a open lane extension for Edelweiss, which is like a whole framework that is meant to make it easy so that you can choose a different target open lane, and then your designs can get pushed all the way through to open lane. Or if you change the target, you can simulate on Verilator, or you can change the target and then burn it onto an FPGA. So Ulov wrote that up on this blog post. That's a good thing to check out. We had some amazing artwork, so really put my artwork to shame, and now I shamelessly use all of his artwork in my own kind of marketing stuff for my course. Maximo Balestrini did some really great stuff by working out how to convert GDS to STLs, import that into Blender, and then come up with great color schemes. And he's done some really nice images, but also some animations that show how the layers kind of come together, and also animations on how these things actually work. At the same time, we had LibreSoc being taped out. So this is interesting because it's not on Skywater and it's not using OpenLane. And I wanted to put this in to just kind of make sure that people can see that it's easy to focus just on one set of tools, but this is really, things are changing, and it's not just happening with those tools. We've got Coriolis 2 that is like an OpenLane equivalent that does automatic design to GDS. It wasn't taped out on Skywater. It was funded by NLNet. It's a whole SoC that's aiming to be an open source computer processor. Yeah, really impressive project. Definitely check that out if you're interested. Luke Layton, who's really involved in that, did a talk for Open TapeOut, and you can check that on this link. So then we've got some SRAM characterization by Andrew Zonenberg. He came up earlier in the Discord chat talking about probes, and he was putting his performance test gear to use in his skills to design this reusable characterization board. So we're using OpenRAM, and we're using it a lot, but we don't really know how it's going to perform exactly on Sky 130. So we really need to kind of be taping out these test structures and doing measurements. We've got OpenRAM. We want to know how fast it can run, how lower voltage, how higher voltage, all this kind of extra stuff. So we've got this daughter board here where the ASIC goes on, that plugs on to this main board here with a FPGA, some memory, an STM microcontroller. And luckily he's got all the parts now. That took a long time to get the parts. The boards were sponsored by OSH Park, so shout out to OSH Park. Thanks, Drew. I've interviewed him. We've done 2 parts so far on the kind of the design of what we're trying to measure, and then part 3 is going to be coming soon, the results. July, I did an experiment. So this is kind of a bit silly, but I'm still quite pleased with it. So this is my VGA clock again, and I wanted to do an OSHW certification of the circuit board, the firmware, and the ASIC all the way down. So on this board, we've still got the flash chip, which isn't open source, but everything else is. So I'm claiming world first on this as a kind of a silly gambit. Feel free to correct me if it's not. And maybe we'll see an OSHW new category for ASICs. Watch this space. August, we had an update from Sam Zeloof, who is awesome. You probably all know him from Hackaday and his YouTube channel. Very, very interesting work, very impressive. And this is his second IC, so he's now at a 10,000 nanometer gate width. So the Skywater is 100, although it's Sky 130, the gate width is actually 150 nanometers. But there's a big difference here. But he's managed to now do 1,200 transistors in his garage. So very, very impressive project. And I'm really interested to see how that goes, what happens next there. One of the really interesting things that is happening through the open source tools is we can put these things on the internet. We can put them on the cloud, we can share the GDS, we can share our designs, and that means we can use things like GitHub Actions. So the Caravelle user project, which is the kind of the submission framework that we use with efabless, we can have a GitHub action that will install the PDK, build the GDS, and then run some tests. And Antmicro have also they've done a lot of work actually. I encourage you to check out their blog. But one of the interesting things they've done is they've got a GitHub action that you can just subscribe to, and that will run a linter on your Verilog. So really good to see this stuff happening. Hopefully we'll have some GitHub actions that you can just attach to your repository, and then when you push your Verilog, you'll get your GDS in a format that's ready to tape out. I know that's part of Tim Ansell's dream. So in October, exciting times, we've got MPW1 silicon arrived. So it took longer than expected because we had the DRC problems in January, and the whole kind of flushing the pipes, doing something new took quite a long time, but we got our wafers back. Then they were bumped. So it's a wafer level chip scale package. So it's a bit like a BGA. So they're going to be a bit tricky to solder, but hopefully not too hard. But sadly, we had some bad news. It was announced on this mailing list, and this is my work in the YouTube thumbnails. Hope you like that. If the story lives up to the clickbait thumbnail, then it's not really clickbait. It's just good marketing. So we had a problem with the clock tree for the management area. So there were hold time violations not detected. And that basically has kind of risen off the management controller part of the MPW1 chips, which is really sad because it means that for most of the designs, we're not able to get a result out of it. Some people have managed to, like analog projects, or if they're not dependent at all on the Caravelle management harness. But one of the problems is that to configure the GPIOs, we need that to work. So my designs in the middle could be working, but I never get access to them because I can't set the IOs up. So efabless were working hard on fix is for MPW2. They resynthesized Caravelle with the hold violations fixed. Chiplgnite, they'd already cut the masks, so they worked on quite an interesting project to fix the clock with a mask edit, and they're going to release some information about that. And then MPW3 was slightly delayed because we had to update our tooling kind of mid-tape-out to take those fixes. And if you want to read more about that or watch the video, then check that link. Okie dokie. So Rapid Silicon got funded. Exciting time in the open source silicon world. Lots of people are doing startups and getting funded. This has come out of the OpenFPGA Foundation. They're taped out this OpenFPGA fabric on MPW1, and that's part of the technology that they support. And they're also involved in the TapeOut World initiative that I mentioned earlier. In November, we had the workshop of open source EDA technology, WOSET, and I was on the review board there. Very interesting papers, a lot of them doing interesting stuff and being able to not only do interesting designs, but then also get those designs taped out so that we can get the results back with the silicon. So again, it's very difficult to pick favorites. There's lots of interesting stuff there, but if I had to choose two, then I'd go for the programmable analog standard cell library. So this is something, the analog and the digital flow are very different. And one thing that people have tried a lot in the past is to have a kind of analog standard cell. so that you've got this library you can build up. And this is a programmable standard cell that uses floating gates. Really interesting paper. And then Open Cache, which is a bit like OpenRAM, but instead of generating RAMs, it generates caches. All the papers and the video presentations are there. So then we had Open TapeOut conference in November. I helped to organize this and I was hosting it, and we had loads of great speakers involved. You can watch it. It was streamed to YouTube, but we recorded it all and it's all there now. We had stuff on, Tim Mansell did the keynote. We had an update on Open Road, which is the core of Open Lane. We had a bit of security talk from David Holton and Joe Fitzpatrick. David Holton taped out a electromagnetic fault injector detector system on MPW2. Very interesting waveform analysis from Lucas Klemmer. Then on day 2, we had an update from Mohammed Kasim, CTO of efabless. Some analog representation, Thomas and Pepine. Then Jean-Paul Chaput and Luke Layton talked about Coriolis and LibreSoc. And then John McMaster finished off with a storming talk about the MPW1 physical implementation. It was super, super cool to start seeing some die shots from open source silicon. And he's done a scanned a micrograph of one of the test chips, and that's uploaded to his website that you can click on and zoom about in. So thanks a lot to him. That got all done very, very last minute. So yeah, thanks to everybody involved there. A little bit more on Coriolis too. So this is similar to OpenLane. It's a fully automated RTL to GDS flow. So again, you put your design in and you get your GDS out. It's kind of more Python based than Tcl based. And Jean-Paul Chaput is one of the lead architects on that project. And he did a presentation at Open TapeOut about it, and you can check that link for more. So MPW3 just taped out on Monday. So yeah, it was a busy last couple of weeks. We haven't had a finalization yet from efabless. It looks like we filled all 40 slots, so hopefully everybody's design gets made. One of the things that changed is that now things are more automated. So you upload your design with a kind of Git sync, then you run a check job, which checks all the DRC, checks your design is the right size, all these kinds of things. And then it does a tape out job. And what that does is it does things like generates the fills and generates the IDs and prepares everything ready to send into the foundry. And everything going well, we're expecting silicon back in April, and all the fixes to the tools went in. So hopefully we won't have any hold or timing problems with this run. So for the course submission, the 0 to ASIC course submission for MPW3, I ran through a couple of my designs from MPW1 because I wanted, I think it's unlikely we'll get them to work, but so I wanted to take them out again. We had 7 designs from the course, and we've got some secret designs here that I can't possibly show you, but actually I can. So this is exactly the kind of thing that I saw when Tim Edwards showed us his first tape out that he did with Qflow. It probably wasn't his first, I'm probably getting that wrong, but there was this gray box here because he couldn't share the SRAM, and this is really fantastic. So now everything is open, we can share everything, fantastic. The multi-project tools were updated. I've had some good contributions from the community into that. Especially I'd like to shout out to Pavel, who helped me with OpenRAM support. So now every time we tape out, we'll put a 1 kilobyte block of OpenRAM in the corner with a wishbone wrapper. So if any one of these designs wants to get access to some fast local cache for a frame buffer or from a FIFO or whatever you want, then you've got it here available, and all the projects can share that. The idea is that each of the projects gets activated one at a time. So you can check out our application there, and I just wrote up a little blog post about it there to have a look at all the different designs. Yeah, there's some interesting stuff in there. My picks of MPW3, we've got a very interesting one from our friend Myrtle Gatecat Shah, who's been super involved with the open source FPGA movement, and they're now getting involved in the ASIC, open source ASIC movement. They did an SoC. They used Coriolis 2 for the place and route. They used NMygen for the design instead of using Verilog. And they didn't use the standard cells. They made their own standard cells using Flexcell. I'll talk about that in a minute, but that's quite an interesting departure. Very interesting to see that. I'm a sucker for nice looking analog. So this is one of my faves from MPW3 and A to D. And it's going to be great when we build up a library of reusable analog IP that we can use to build our projects with. And something I'm really interested to find out about is this RISC-V Arduino compatible project that is aiming to make RISC-V compatible Arduino project. So hopefully I'll find out more about that later. I've invited all these people for interview, and hopefully that will get posted on my channel soon. So Flexcell, this is a project from staff at Chips for Makers, and the idea is you can load in the DRC rules from the process design kit, the PDK, and then it will generate you a library of standard cells, all the AND gates, the OR gates, all the kind of the basic digital logic stuff that you can then use in it for a digital design. And hopefully that's going to work with OpenLane, and it works with Coriolis. So I'm suggesting that we make a 10,000 nanometer standard cell library for Sam, and for his third chip, he can start taping out some digital design. So I haven't told him yet, but watch this space. And then in December, we've got MPW4. So we've got 2 tape outs really quickly. So there's probably going to be quite a lot of space on that because everyone just taped out on MPW3. So if you've got an FPGA design handy and you want to try this out, now is a great time. Skywater and efabless are working on adding ReRAM. So that's adding a new layer into the Sky 130 stack up that is going to give us resistive random access memory. And I don't really know much about that at the moment, except that it's non-volatile. So that's going to be quite an interesting new development that we all get access to. So what's happening in the future in 2022? Google, so in Tir Mansour's keynote for Open TapeOut, he mentioned there's going to be more shuttles. So initially they said 6. We've had 3 this year, but now we've got confirmed another 4 next year and another 3 on another process. So that is great news. They're going to reveal another foundry. They're adding more PDKs, so a 90 nanometer node, another 130 nanometers, and a budget 180. And we're seeing more and more investment in this place. So I already mentioned Rapid Silicon. Zero ASIC got funded. Zero ASIC isn't related to my course. That's one reason why I changed the name of my website. That's a different project. They're active on LinkedIn. Go and check them out. And efabless are also raising money. Now, I can't remember who suggested it, but somebody suggested that we may be able to salvage MPW1 by overriding the GPIOs. So if you remember, the Caravelle Pico RV32 configures the GPIOs to set them to be inputs or outputs, and they're set up as a big, long shift register. So if we could zoom right in and cut some lines and then solder on some new lines and then override them with an Arduino, we could maybe set up a working configuration for the IOs and then get access to the designs inside. So I thought, okay, yeah, that's a cool idea, but when am I ever going to do that? And then at the Hardware IO Security Conference, I was introduced to Olivier, who I happen to already know on Twitter, and he's really interested in doing a collaboration where we take some chips to his lab where he has a focused ion beam, and we'll try to do this edit on the chip and get it to work. So watch this space. And this is actually quite interesting because he's very interested because he's only ever works with the chips and he's reverse engineering them. And this is a time where we have the design, the GDS, and the chip. So he's able to kind of do this connection front ways and back ways. So a little note on community growth. We've got 2,000 people on the Skywater Slack. You can join here to learn how to get more involved. And we've got 240 public projects with the design, the GDS on the efabless website. And this is a really interesting and useful resource, and I know that Mitch Bailey is using that resource as a way to train an EDA tool that he's working on at the moment. So that's the end of my talk. I hope you enjoyed it. Please get involved. You don't need to be a full-on ASIC guru. I'm certainly not. You can contribute to documentation. You can contribute to the software. The next TapeOut is going to be on MPW4. There's probably going to be a lot of space on that. Feel free to connect with me. Join on the Hackaday Discord. If you've got any questions, go here for the slides to check all the links. You can sign up to my newsletter, which is about keeping up to date in the world of open source ASIC and information about my course. And of course, you can connect with me on Twitter. So thanks very much for watching my talk, and I'll see you online.